Grade your exams. I'll try to do that today so that you have an exam on Thursday. And there's a new homework I posted, which is due on Tuesday, following Tuesday. Nine. Midterm 2. And there was a discussion about midterm 3 also, which we'll talk about after Thursday. Are you guys still up for it? Yes.
For the midterm too, this room's 9.
Oh, yes. I think so. There is usually a chart there. I never see it occupied. So let's have it in this room. By any chance, we are only 3-4 of us. By any chance, if it is occupied, easiest is to go into the launch, but I think we can find another room. So let's not try to reserve a room. And so that's, I think for 4 students, it's not okay. Reasonable? Okay, yeah, so we meet in this room. So in 486. So we have talked about Poly matrices a little bit last time. So, Poly. Matrices, and we said that it's pretty much all its characteristics are decided by what is called the algebra of Poly matrices. Basically tells if you multiply 2 of them, what do you any 2 of them. Poly matrices are Hermitian. That means to say that sigma I dagger is equal to sigma I. They're also unitary. So first let me say they're traceless. 0. So this is Hermitian. Traceless. And they're also unitary. What's the unitary matrix?
This main diagonal one.
No. Unitary matrix. What is a unitary? What's the definition of a unitary matrix?
U equals, or U dagger is the identity. Is one of them.
U dagger is identity. Yeah, that's close enough.
It
Yeah.
preserves the matrices of Hermitian property. Like, using them as transforms. So,
Yeah, U dagger is equal to inverse, which means that U dagger is equal to U inverse. So the inverse of the matrix is Hermitian conjugate of the matrix. That's what it's right. Yeah. So that's exactly right. Okay. So sigma I, sigma dagger is equal to 1, which means that sigma dagger is equal to the inverse of the matrix, and that means that this is unity. And say, and polymatrices are Hermitian traces, all three of them. And again, as of now, even though we in between here and there have introduced polymatrices, I haven't ever told that what is the structure of this polymatrices. They are just three symbols, right? Sigma 1, sigma 2, sigma 3. But most often we work in rectangular coordinates. Similarly, we work in a particular basis, and in that particular basis, there is a representation. So let's talk about so let's say, or before that. Yeah. So let's have, we need some basis, right? So let's find the, let's say a representation of polymatrices. I'll start from one and go into the other. Okay, and that should give you an idea of, I can do it in many, many ways, infinite ways actually. So let's say so this will be sigma 1 is equal to 0, 1, 1, 0. Sigma 2 is equal to 0 minus pi, 0. And sigma 3 is equal to 1, 0, 0, and so on. Okay. Typically, the moment you see a diagonal matrix in a combination of matrices, it immediately means that this representation is in the basis of the eigenvectors of sigma 3. Okay, so that's it. So let me state that in the basis, the eigenbasis of sigma 3. Okay. So immediately it raises the question, what is the eigenvalues and eigenvectors of sigma 3? So what are the eigenvalues and eigenvectors of sigma 3? What are they? What are the eigenvalues of sigma 3?
Minus
1.
1 minus 1, right? It's already diagonal. It's obvious. So sigma 3 prime is equal to plus minus 1. What about sigma 3 prime, what is the eigenvector associated with first eigenvalue?
1, 1.
1, 1. Why do you say that? Because you would say look for 1, 0, is it?
Because unnormalized.
Right. This is x square, this is z1 square. Z1, Z2 is equal to 0, 0. Correct. So you would say that Z1 is equal to 0. Right? And is that correct?
Yeah.
Oh no, that's wrong, right?
This
This is the matrix itself. I have to subtract the eigen eigenvalue, right? So 1 minus 1 is 0, minus 1 is minus 2. Right? So Z1, I don't learn anything from here. Here I do learn that Z2 is equal to 0. And Z1, I need it to be normalized. So Z1 square has to be equal to 1. So I immediately say that this is 1, 0, up to a magnitude is 1, but that doesn't give me tell me anything about the phase. So in general, this is e raised to I alpha 1. Let's in this discussion to avoid, I think I've stressed enough that there is a phase that is missing, and we choose the phase to be 0. Just because I want to emphasize the characteristics of the eigenbasis. Okay, is that clear? So that's 1, 0. Similarly, what is the eigenvector for sigma 3 prime is equal to -1, the other eigenvector? Oops, move it. What is the other eigenvector?
Zero,
0,
negative 1.
0, negative 1. So again, it will be, I have to subtract -1, right?
2,
So 1 minus 1, so it is 2 times 0. So -1 plus 1, so this is 0, 0 times Z1, Z2 is equal to 0. Correct? So Z1 is surely equal to 0. But Z2, I don't know anything about it, but I want it to be normalized. So Z1 is 0, so Z2 square, magnitude of Z2 square is equal to 1. So Z2 is e raised to I alpha 2. Correct? But it's plus 1, no minus, right? And I think the -1 you're confused probably because there is a -1 here. So let's check this. So there's a small confusion here. Does it really work? Right. And with a phase here, but I've set the phase equal to 0. Okay. And it doesn't have to be the same phase. It'll be different phases. So let's see if this really works. So 1, 0 times 1, 0, 0 minus 1 is equal to 1 and 0. So that does work. And 1, 0, 0 minus 1 times 0, 1 is equal to 0. And this is -1. It doesn't seem to give you the same vector, but then it is needed that we have to pull out the eigenvalue, right? So it has to be eigenvalue multiplied by the eigenvector. So that's the -1 that should be. Okay. Okay, clear? So now that we have these two vectors, remember our in the very first couple of weeks we talked about orthogonality and normalization and completeness. So let's see orthogonality. orthogonality. So let's do sigma 3 prime is equal to plus, and sigma 3 prime is equal to false. It should be plus 1. If you allow me, I think there is no ambiguity. If you don't write plus. Okay. What is that equal to? And let's also do sigma 3 plus is equal to minus that equal to, and each one of them. What is this? This is 1, 0. That's also 1, 0. That's 1. And since it should be auto normalization, since it's normalized, that's perfectly fine. What about this?
Zero.
So it is plus. So it is since it is written the other way, I have to. This is complex conjugation, right? 0, 1, 0. This also comes out to be 0, and that comes out to be 1. Okay. So very clear. And if this is satisfied, that's called orthonormal, right? Whenever they are the same, it is non-zero. And if they're not the same, plus or minus, minus or plus, then it is 0. Yes, please.
So orthogonality and orthonormal are different.
Orthogonality means this could have been any number.
Okay.
So for example, the best, this is also an eigenvector, right? That's also an eigenvector. If you check it, it will actually give you 2 times this. Okay, that's also a vector. So if you were to do that here, you will get a 4 there. So it just has to be non-zero, right? But you normalize it by distributing that 2 into these 2 vectors. So that's called, so once it is orthogonal, make it such a way that this is 1. Is that clear? What I said? So in principle, like for us, it is orthonormal. Okay. Notice how this is like a dot product, right? I mean, we have done this eigenbasis where we had this vector E I and vector E. Let me write this here. And vector E I. Remember, we used to have this, right? This is the dot product of these 2 quantities. That's the analog. Like I have an eigenbasis and I'm taking a dot product. This dot product has been shown up this way. Okay. There was also a construction using eigenvectors, which were completeness, right? Instead of I and j being the same, we said, what if this was I and this was also I, and no dot product between them. Right? Remember, there is an outer product we used to say, right? There are 2 vectors. Right? Now that was called the completeness relation. So what is that here? Any questions? Okay, completeness relation is take the eigenbasis, like two eigenvectors, there is only two in our case, and sum them up, like 1, 1, 2, 2, only two of them. So what that means is that sigma 3, what we have to do is outer product. So this is plus, this is an outer product. Here I'm multiplying the two vectors with the opposite sense of the dot product. And let me write it very far away so that there is no confusion, otherwise there is too much clutter. This is one construction. When I multiply these two, will I get a number? Will I get a vector? Or will I get a tensor? In our case, a matrix. Like, will you get a vector, number, or a matrix?
You get a matrix.
Matrix, right? So this is a column vector. That's a row vector. When you multiply a column and a row, you get a matrix. Okay. Same thing, another matrix down here. So this is sigma 3 prime is equal to minus, and sigma 3 prime is equal to minus. Is that clear? Let's see what this is equal to. Okay. Yes.
So you only take the orthonormal?
No, this is not, see, notice orthonormal is the opposite way. Orthonormality gives you a number.
Yeah.
I'm building a matrix now. So maybe what you're asking is that I take plus, plus, and a minus, minus.
Yeah.
That's what you
The
mean.
ones-
Yeah. I don't take the mix up
Okay.
because it's a sum, right? I is equal to 1, I is equal to 2, it's a sum. Right? So that's what I'm building, right? So that's equal to, let's construct that. So this is 1, 0, and 1, 0. Right? That's the first one, that's easy. And the second one is 0, 1, 0, 1. Is that clear? What is the first matrix? What is the first one? This is 1 times 1, 1 times 0, 0 times 1, and 0. And then you do again the same thing. This is 0, 0, 0, 1. Notice how it works. Even here, it was the same thing. If you were to multiply these two vectors, only one survives in the diagonal. Second diagonal gives you the second diagonal element. If there were 5 eigenvectors, you will get 5 pieces of 1. And this is 1, 0, 0, 1. It's the identity. And that's the completeness statement. This plus this should give you 1. Okay? So this is an identity matrix. Okay. So it's all very straightforward. It's just properties in a sense, but now we are going to use this property. Okay. Or let me do one more thing. Yeah. Okay. Clear? So eigenvalues, eigenvectors, orthogonality, and completeness of sigma 3. Let's now do sigma 1 also in the same manner, and then I will do something using the book. And then we'll mix things up. Or I'll write one in the basis of the other. Okay, so let's go to the eigenvalues. And vectors. Sigma 1. What are the eigenvalues? Sigma 1 prime. Prime, remember, are the eigenvalues, right? What are the eigenvalues?
1, 1.
One,
The
one.
eigenvalue, yeah, the eigenvalue is just
One. There's only one eigenvalue?
there are 2.
Two. So both are one?
I believe 1 is
1, 0.
1, 0. Find it.
yeah, it's 1.
1 and -1, right? So it's the same eigenvalues even now. It's plus or minus 1. This just happens to be. It doesn't have to be the same eigenvalue, but it's the same. Turns out. What about the eigenvector? What's the eigenvector sigma 1 prime is equal to plus 1? That's it. So you would do now that this is 1, 1, 1. No, I'm subtracting, right? So this is minus 1. That's it. Eigenvalue equation, and this gives me that z1 minus z2 is equal to 0. So z1 is equal to z2. Right. So it's not equal to 0. Both are the same, but z1 magnitude squared plus z2 magnitude squared is equal to 1. That gives me that 2 times both are the same. So z1 squared is equal to 1. So z1, magnitude of z1 is 1 over root 2 up to a face. z2 is the same, so it is 1, 1. Right? So up to a face, this is 1, 1. Okay. But again, remember, all this is in this representation. And this is in the basis of sigma 3. Okay. So, and what about the other eigenvector? So other eigenvector will be do the same thing again, right? Minus 1. So it is 1, 1, 1, 1. It's equal to 0. Again, the same idea, but now z1 is equal to minus z2. Right. So, clear? So c1 prime is equal to minus 1 over 2 and 1 minus 1. Check it. 0, 1, 1, 0 times 1, 1 up to root 2 comes out anyway. So this is equal to 1. That's 1. That's plus 1. And 0, 1, 1, 0. 1 minus 1 is equal to minus 1. And 1. Minus 1. Up to a face of up to a constant. Okay, let's Okay, yes.
One and negative one is also like, as far as eigenvectors go, -1 and 1 would be.
That is also because up to a face, right? E raised to I pi, right? It's up to a face, e raised to I pi times 1 minus 1 is equal to e raised to I pi is minus 1. So that makes it minus 1, 1. That's also, and if you want to normalize it, it's 1 over root 2. Yeah, e raised to I pi by 4, you can do various, many steps. So up to a face, you cannot help it. Okay, so that's so these orthogonality or orthonormality, right? Orthonormality. Again, do the same thing. Sigma 1 prime is equal to plus. That's equal to 1, right? Because I'll get it 2, 1 times 1 times 1 times 1, I'll get it 2. There's already a 2 when I square that, so it's actually 1. Sigma 1 prime is equal to plus, okay, and sigma 1 prime is equal to minus. Now it is 1, 1, and 1 minus 1 is 0. And remember, this should be complex conjugated. If you haven't encountered any of these eigenvectors that are complex numbers, if they were complex numbers, when you write it as a row, it should be complex conjugated. So that's equal to 0. Clear? Completeness, are these complete? Like sigma 3 we found were complete. Are these really sigma 1 eigenvectors, are they complete or not? So let's check. So it is this time sigma 1 prime is equal to plus that's equal to, both have a 1 over root 2, so I put a 1 over 2 in the front. 1 over root 2 square in the front if you want. And the first one is plus, so it is 1, 1 multiplied by 1, 1. And plus. And 4 over root 2 square 1 minus 1 and 1 minus 1. So it's 1 over 2. And this is 1, 1, 1, 1. That's all. 1. And this is 1 over 2. One minus 1 minus 1. And notice that the non-diagonal terms cancel out. The diagonal terms 1 by 2 plus 1 by 2 add appropriately, very finally to give you a 1. So it is complete. Okay, clear? Okay. So that's just a simple exercise on eigenvalues, eigenvectors, and also sampling. But now let's mix things up. Like once we have two eigenvalues, it's like saying that we have a rectangular coordinate system and a spherical coordinate system. I can write a vector given in rectangular coordinates into spherical coordinates. It's the same vector, doesn't change, but its representation changes. Like it has a new way. It looks different. Okay, so let's write. Change the camera before this. Yeah. Let's write sigma 1 or sigma 3 in the eigenbasis of sigma 1. Okay. Let me just very quickly, just to give you a feel for what we are doing, let's think of a vector like a position vector A. Let's take a vector A. Right? A is equal to, let's say, 3i plus 4j. That's a vector existing in rectangular coordinate, right? The moment I say I and j, it's rectangular coordinate. But what if I want to convert this into spherical coordinates, okay, or polar coordinates? Let's say what I would do is I'll start with vector A, right, and multiply it with 1, right? It's a dyadic that I do. This is a completeness relation, and I do that. Yeah, that's good enough. Okay. And then what I do is, this is nothing but what is completeness relation in spherical coordinates or polar coordinates? It's rho hat plus phi hat, right? And then I will do A dotted with rho hat and so rho hat plus E dotted with phi hat and phi hat. Is that clear how the completeness relation played an important role when I'm going from one to the other? That I just got to multiply by 1. And then of course comes, since A has 2 pieces, so this will be 3 times I hat dotted with rho hat plus 4 times j hat dotted with rho hat in the direction of rho plus 3 times I hat dotted with phi hat plus 4 times j hat dotted with phi hat. Is that clear? And typically we know that I hat with rho hat is cosine theta, this is sine theta, this is cosine theta, sine theta, and so on. Right? That's the breakup in that. But this is good enough. Right? So at least as a concept, it should be very clear. But we now want to do the same. And this is a vector. If it's a matrix, you will multiply on the both sides, 1 to 1. Right? So that's what we want to do. We are working with matrices now. So let's see how we proceed. So we will start with sigma 3. Sigma 3 has to be written, right? We are interested in sigma 3. So let's start with sigma 3. What we are interested in. I want it in the eigenbasis of sigma 1. So first of all, I write 1. Right? I multiply a 1 on both sides. That's perfectly fine. But each of this 1 is this one here, sigma 1, all right? That's the total eigenvector. So that's this. So this is equal to sigma 1 equal to plus sigma 1 equal to plus sigma 1 equal to minus that whole thing is 1. Is that clear? And then I do sigma 3. Let me, if you allow me to write that here, sigma 3. And then again a sigma 1 plus any questions? That's equal to. So there are two pieces here, and in between there is a sigma 3, right? So 2 times 2, there will be 4 terms with sigma 3 in between. So I'm going to arrange them this times this times that, and so on. I'll write them as 4, but I'll write it as a almost like a matrix. So this is sigma 1 is equal to plus. Then I have sigma 1 equal to plus. This multiplies by sigma 3. That's sigma 3. And then comes sigma 1 plus. So that's a number now, right? This whole thing is a number, and then this makes it a matrix. This whole thing is a matrix. This one piece is a matrix. And let me write the next piece, plus. Let me take sigma 1 plus itself. Plus 1 minus okay. It's not really a matrix because these are 4 terms, right? But each one of them is a matrix. Is that clear? Because there's a number, this multiplied by that is a matrix. So it's a sum of 4 matrices, but it's nice to see this as components of a single matrix also, which I will highlight in a minute. Okay. Let's calculate these numbers. Right? There are 4 numbers involved in this. Let's calculate this. Okay. let's do sigma 1 is equal to plus, sigma 3, sigma 1 is equal to plus. That should be a number. Sigma 1, right? Sigma 1 was, both are sigma 1, so it's 1 over root 2 squared. And that is 1, 1. Sigma 3 is 1, 0, 0, minus 1. And 1 minus 1. That's about 1 over 2 times 1, 1. And that's 1 here. 0, 1, so that's 1 here. That's 1 over 2. Why did it come out 1 over 2? No, it is 1, right? So,
Two things.
yeah. So, so let's do the same thing. The next one, sigma 1 is equal to plus, sigma 3, sigma 1 is equal to minus. That's 1 over root 2 squared, 1, 1, 1, 0, 0, 1, and oh, what did I do? There's a mistake. Yeah, there's a mistake here, right?
Yeah.
1, what did I do? Yeah, 1, 1, 0. What did I do? Sorry. Yeah, this should have been plus, right? This was sigma 1 plus. Right, so this was a plus. And then this would have become minus, and this 0. And now there is 1 minus 1 here. And this is 1 as we did just now. What about sigma 1 is equal to minus 1, sigma 3, sigma 1 is equal to plus. That's the next one here, so that's 1 over root 2 squared. Sigma 1 minus, right? So this is 1 minus 1. One. Sigma 1 equal to minus plus 1. Square 1 minus 1. One, 1. Zero. Okay. So out of these 4 pieces, there are 4 terms in this. 2 of them are zeros and 2 of them are 1. But if you think of this as a matrix, right? It is these ones that are coming out to be ones, not the diagonal ones. So let's so sigma 3 then is equal to it's equal to sigma 1 plus, and this is sigma 1 minus this thing can be written in this form. Okay, or maybe I can make it even better. Let me write that more explicitly. Sigma 1 equal to plus, sigma 3, sigma 1 is equal to plus, sigma 1 is equal to plus, sigma 3, sigma 1 plus. Remember, each term in that is a matrix. Is that clear? Like that construction. It is equivalent to saying this is what we mean by a matrix. This should be thought of as when we say that a matrix A is 1, 2, 3, 4. We often say this, like, or when we say a vector, let's say B is equal to 3, 4, without any basis vectors. What this means is that this immediately we say that, oh, this is the way of writing, but this is actually 4J. That's what we mean. That is a eigenbasis in our mind. Like if it is always we are in the same basis, that's what we mean. But what about a matrix? There is a similar construction for a matrix. What it means is that this is equal to 1 I hat, right? It's a matrix, plus 2 I hat, j hat, plus 3 j hat, I hat, plus 4 j hat, j hat. Is that clear? That's what a matrix means in general. If you want to write it in the form I have written there, so it is I hat, j hat, 1, 2, 3, 4 times I hat, j hat. Okay. But if you're always in the same eigenbasis, then you say that I don't want to write that. I'm happy with just the components. These are the 4 components in the eigenbasis of rectangular coordinates here. Is that clear? Now, since I mixed up the bases, I said I'm going to find the sigma 3, which is usually written in the eigenbasis of sigma 3 itself. I'm writing it in the eigenbasis of sigma 1. Okay, so it looks like this. So this is equal to this. So that's equal to sigma 1 plus 1 minus, this is 0, 1, 1, 0. That's what we found there. And And now if we agree to the fact that, okay, from this point on, whenever I say anything, I'm going to be writing only sigma 1 basis, then I can drop it. And then you notice this is sigma 3 in the sigma 1 in the earlier basis. Sigma 3 in sigma 1's basis happens to be sigma 1 itself in that other basis. So it has no meaning. Like it being sigma 1 has no meaning because this is a new basis. Right? This is not sigma 1. This is sigma 3 in this basis. Okay. What will remain same, I'm not going to do this because we have to do this the whole thing. So now, yeah, I think this is in your homework. Okay. What you can do is, now I found sigma 3 in sigma 1's basis. What will sigma 1 be in sigma 1's basis itself? Like think of this, like you need the 4 pieces, right? Yeah, these 4 pieces, you need sigma 1 inside. Can you do that? It is possible to do that in your head. If this was sigma 1, what is the right hand side? So we want to find that. So let's find that. Yes.
Yeah, I mean, I think it's the opposite of, like, I think it's 1, 0, 0.
1, 0, 0, 1, because sigma 1 acting on the eigenvector of sigma 1 is sigma 1 itself. Right? And then they are the same, right? They are orthonormal. So that is equal to 1. So this will be equal to 1. This will give me sigma 1 times sigma 1 minus is sigma 1. But these two are by orthogonality 0. So this is 0. So by orthogonality, this will be equal to 1 or 0, right? So this is 1, 0, 0, 1. Since we are writing this in the new base, let's leave it like this. Okay. So let me say, yeah. So in sigma 3 basis, we have sigma 1, sigma 2, sigma 3. And this is the default basis. Whenever no one talks about which basis you're talking about. If you have any confusion on you're reading a book, and now I've told you there are so many bases. When you're reading a book and you're not sure what this basis is, it is in sigma 3 basis. It's like the rectangular coordinate system in a textbook. It's taken by default and everyone works in rectangular basis, but it's not necessary, especially in quantum mechanics. We don't work in this basis all the time. But this is equal to 0, 1, 1, 0, right? So this sigma 3 basis, 0 minus pi, 0. And this is 1 minus 1, 0, 0. That's clear. And now we work in sigma 1 basis. And we have found that sigma 1 actually is 1 minus 1. In fact, always in its own basis, it will be diagonal. Right? A matrix in its own basis will always be diagonal. Sigma 3 we have found is 0, 1. This remains as an exercise for you. You have to complete this. This will come out to be exactly 0 minus I, 0. And if you were to do the algebra of these three, they will remain the same. Whatever you do to the representation, the algebra of these three matrices remain perfectly fine. These three are solutions to the first algebra that we wrote. If you multiply these two, they will always give the third matrix in the right way. One, it is very clear that sigma 3, sigma 1, and then there should be a sigma 2 basis also, right? That should not be any confusion there, right? One can do this in sigma 2 basis also, clear. In fact, you can do this in the basis of any 2 by 2 matrix. Right? Pick your favorite 2 by 2 matrix, find the eigenvectors, and you can write your three matrices, and they will satisfy their solutions to Pauli matrices. Is that clear what I said? You can pick any 2 by 2 matrix and do that. Now in quantum mechanics, what you do is that there is a 2 by 2 matrix which acts like an operator. Right? It measures something and it gives you an eigenvector. It collapses into an eigenvector, and then you put in another measurement. Again, it collapses into something, and it's the projection of one into the other that is the measured quantity. We'll talk that a little bit more in the next class. So to that, let me build a little bit. Any questions at this stage?
Yeah. So when we started it, we took it as in the sigma 3 basis, like in the beginning.
Yeah, in the beginning, the actual Pauli matrices, which are the popular ones, they are always written in sigma 3 basis. That's what you're doing. That's the analog of rectangular coordinate. By default, whenever we say Pauli matrices, they're not really Pauli matrices. It's a representation of Pauli matrices in the sigma 3 basis. These are the ones that we always use. But that's just one possible solution. Okay. And now let's build a whole set, right? I mean, so it seems like it is not at all unique. So let's consider let's construct a vector sigma. Right? And so this is now we are in the basis of sigma 3. Okay, this is sigma 1, the first Pauli matrix, multiplied by I hat. That's a space vector, right? Sigma 2 times j hat of sigma 3 times k hat. Okay. This is a vector whose components are matrices. Like sigma 1, sigma 2, sigma 3 are matrices. So this is more explicitly 0, 1, 1, 0 in the I hat direction. The matrix in the I hat direction. Typically we have numbers, right? Minus I hat 0 in the j hat direction plus 1, 0, 0. This one. K hat. Okay. That's a vector. Keep it. Let me think of another vector or R hat. Yeah, a magnetic field which is pointing in a certain direction at one point. So this is the same as the magnitude B times R hat. So this is a uniform magnetic field and it is pointing in the r hat direction. So that's one way of looking. That can be written as b times r hat. I want it in rectangular coordinates. So like this. Right underneath. So this is b times sine theta times cosine phi plus sine theta times sine phi that direction plus cosine theta the k. So that's a spherical polar representation of the unit vector r hat. Clear? Let's construct this matrix. That's a vector, that's another vector, but this vector is constructed out of a matrix. So let's see what is the dot product of these two vectors. That's equal to, I will multiply this times this, this times this, this times this, right? So b is common in the both, so this is b times 0 sine theta cosine phi, sine theta cosine phi, and 0. First matrix. Second matrix is plus b 0 sine theta I times sine theta sine phi minus I times sine theta sine phi 0 plus we good? Those are three matrices. I can combine them, right? I can add them. There's a 0 here, 0 there, cosine theta, right? So I have a b times cosine theta. There is a 0, no, there's a sine theta cosine phi, and this is a 0. So this is sine theta is common. And there is cosine phi plus I sine phi.
Minus.
Minus no, this one, right? Bottom.
Oh, bottom.
So is that correct? And this one, you're right, is minus. So it is sine theta cosine phi minus I sine phi. And finally, it's 0, 0 minus cosine. That's the same as b times cosine theta sine theta cosine phi minus I sine phi is using that complex representation. This is minus I sine phi, exponential of I phi. This is sine theta e raised to I phi, and that's minus cosine theta.
E to the minus I phi.
Again,
Oh, okay. E to the minus I phi cos phi minus.
yes, where I've used cosine phi plus I sine phi is equal to e raised to I phi. And this will be our Hamiltonian. Notice that if this was angular momentum, this is the interaction energy of a magnet with another magnetic field. If you, when you place a magnet inside in another magnetic field, it is the magnetic moment that multiplies with the magnetic field. And magnetic moment is nothing but the angular momentum of it's constructed in terms of the angular momentum. And we'll start from here next time. So we will find eigenvalues, eigenvectors, which we will just assume, and then we will ask what if we measure once the magnetic moment. So if we have a beam of magnetic moments, a lot of magnets, let's say, put in, and there's a magnetic field, they all try to align with the magnetic field, correct? So afterwards, again, we select another one. What will happen to that? What is the probability of finding magnets in one over the other? Yes.
So you mentioned the magnetic moment,
Mhm.
and so I'm always used to seeing that in terms of spin,
Uh-huh.
and then so I guess the spin is just written in terms of these Pauli matrices.
Yeah.
Is what-
So let me tell it in a minute. So,
Let's see the angular momentum come out.
so this is your magnetic moment. Right, let's say sometimes it's the magnetic moment is how do you know magnetic moment? What is magnetic moment? How is it introduced to you?
I always kind of think of it in dipoles, I guess.
Yeah, dipole, magnetic dipole moment. Which dipole? Not electric dipole, magnetic dipole. So the magnetic moment, you will define it as, suppose you have a current carrying wire. This is one elementary definition, right? This is a current carrying wire. If it has an area A, the magnetic moment will be I times A times the unit vector, which decides the area vector, right? Let's say this is a perfectly circular loop. So this is Q over some time period, right, T, and then there is pi r square. That's n hat. So that's your magnetic moment. And let's see, Q, V, R. So velocity of a charged particle going in this here, this will be 2 pi r over t. The velocities of something going in a circle. Think of all these charges going in a circle, right? So that's equal to Q times Q over 2 times 2 pi r over t times r times n hat. Very naively speaking, in a perfect scenario where everything is in a circle and that the charged particle uniformly going around it, but it's a true statement. So this is 1 over 2, and let's say, so this is Q over 2 velocity times R and n hat, right? If we multiply by an m there, m in the denominator, right? So I have Q over 2m times R, let me write this is R, vector R, position R, let's say, cross MV.
The M is the mass.
M is a mass, right? Mass of the charged particle that is moving in a circle. Think of a single charged particle moving in a circle. That's the best. That's angular momentum now, right? So you say, oh, that's angular momentum. So this is, so magnetic moment is directly proportional to the angular momentum of the particle. Right? That's good, right? That's a way to look at it. But now, let us say, that there is no motion, right? You sit on the charge itself. You go and sit on top of the chart, and angular momentum should disappear. Right. And it turns out that some particles, they don't disappear. That's called a spin. But it cannot have any velocity reference, because otherwise it will go to zero. So you say that, oh, that's not the complete story. That is an additional thing. So that's F. Okay, that's spin. Okay. This survives even when velocity is zero. Is that clear? But this is not how, yeah, this is not complete, let's say. That's clear? Yeah. Okay. And since it's now behaving like an angular momentum, this has to have the algebra of the angular momentum. And Pauli matrices satisfy that angular momentum algebra. Okay. So they don't have any velocity reference, but they are matrices. Some quantities that have all the algebra of angular momentum, but they are velocity independent, has no position dependent, no velocity dependent. Yes.
So this angular, the angular momentum has orbital, I should say the total momentum is orbital momentum, angular momentum.
Now, orbital momentum spin,
And spin.
and
Okay.
the total is this. So the statement typically is, I think this is what you're looking for. L plus F.
Okay, yeah.
So this is orbital. This is spin. And this is angular momentum, or total angular momentum.
Thank you.
So if you sit on the particle, then this is done. Or it's called the intrinsic angular momentum. Sometimes they call it that. You guys need to run. Yeah, we'll go over it.
For midterm, you need to prepare up to here.
Yes, why not? Is that, no, this is actually, this homework is due afterwards, right? Yeah, for midterm until last Friday, that's it. Like until the eigenvalues, eigenvectors. But not. Thank you. Yeah.